n equal to ej omega naught n. So some sequence like this. Then moving through h, we get y of n equal to h of omega h of omega naught times e j omega naught n. Okay. So this is the two theorems we proved the first day. Maybe we should spend some time to understand this part a little bit. So what this really mean? Because this is a complex exponential signal, so maybe hard to recognize them at first. So now I'm going to see. So now consider another one here. So 1, first 2, and now 3. Now let's say I'm going to look at the signal xn equal to something we're more familiar with, namely the signal of cos of omega naught n plus, maybe just take that one. Right? So this is a very simple cosine signal. Right? This is a simple cosine signal. And it can be written as, I can use Euler formula, so I can write this thing here is equal to 1 over 2 e j omega naught n plus e minus j omega naught n. So I consider this signal, which is not hard to imagine, right? It's oscillating signal with a certain frequency, omega naught. Okay? So I fix omega naught, I have that signal. And it can be written in this. And now I'm going to put this signal through the system H. Then I would get our yn is going to be equal to this 2. So it's 1 over 2. And I'm going to have here h of omega naught e j omega naught. Are we okay with this? Okay, e j omega naught plus h of minus omega naught e j omega naught n. Okay, so that's what we get out here. So we have that signal then, and one thing we know, so let we assume, so now assume that Hn, so the thing I'm trying to do here is, this is a complex signal. The filter is complex, and this may be a complex signal. But now I want to look something more realistic, something that the signal maybe when we collect is a real signal. So this is a real signal. And I assume that the filter is also real. So then the output is also the real signal. And I want to see what that real output look like. Alright, so that's what I'm trying to do. So assume that Hn, this thing here, is real. Is a real filter. That means each of these numbers are real. Then it's not hard to show that the h of minus omega is simply equal to the h of omega, but you take the complex conjugate. Everyone alright with this complex conjugate notation? Okay, now you've seen this notation before. So what we have here and is a complex conjugate number. There's a number here plus a complex conjugate. Right? Because this is complex conjugate and this is a complex conjugate of that. Okay. So what happens when you have two complex numbers that is complex conjugate each other? You add them and divide by 2. You got a real number. And what the real number would be?
It's a real one.
The magnitude that multiply with the Ej of the phase of that H omega. Right? Any number, and maybe you can see here. So if I have the Z here, then it's always equal to R times Ej of theta. Right? Where this is a theta here. Right? So that is the complex number. And what we have here is that number Z. So I add Z with its complex conjugate. This is the Z complex conjugate. Right? The complex conjugate is exactly the one that here is the real axis and here is the imaginary axis. Okay. When you add these two numbers together, you got these two vectors, and you divide by 2. So what you get out is this real part. What you get out here is the real part of this complex number. Right? Z plus Z minus 2, so Z plus Z complex conjugate over 2 equal to the real part of Z. And what is the real part of Z? If I take this, so this is equal to R cos of theta plus JR sine of theta. So the real part of theta is simply equal to R times cos of theta. Right? So that's a simple. So now, when you take this, so this number is equal to that, multiply Ej this, and now this Ej join this thing here, go to exponential, and when I take this trick there, I got this. Okay, so everyone see that. Alright. So this thing giving you something quite important to remember. Very important. If I take a signal that is sinusoidal, so maybe you can draw here. So the sinusoidal signal, but remember our signal is a discrete. So maybe we have a sample, some random location sample here. Right? So I have this input here. I put it through the system S, the system H, I mean. Then what I get out here is another sinusoid cosine signal where the sample are now. And two things happen. The sinusoidal signal, and this is one particular frequency, omega naught. Right? This cosine signal goes through H, two things happen. One, the amplitude of this thing here get magnified by H omega naught, which is the absolute value of this. Second, this thing here gets shifted by this. Right? So a filter, when I design having this, a complex